Let's get started. Right. Okay. Come back to lecture 4. Where today we're gonna introduce models that we're gonna consider in this class and look for explicit solutions. Okay. So the topic on models, we are following Cessna chapter 8 and Yeoman's chapter 2. And so the model that will be of most interest, and is seen also on the problem set already popping up, is the Ising model. In this case, I'm referring to the so-called spin case. The idea is the Ising model that we consider.
Should I tell us it all?
Well, typically people will vote in, so let's see. Very lucky. So let's consider a two-dimensional lattice of lattice of n sides. Now, on each of these lattice points, I can I have a spin that can either point down or can point up. Just as a better visualization, let me add color. You may not see my, so like pointing down, coloring light blue and the other one. And so I describe my system by the states, by the two state degrees of the spin. At any site I as I pointing up or down, so +1 or -1. So these are two degrees of freedom. And then I describe this system by Hamiltonian, where I have an interaction term between spins, Si and Sj. And I can apply a magnetic field that is acting on each individual spin. So that's, the J is called coupling or exchange energy. And this is the sum of our nearest neighbors. And this is the external field. And this is a drawing for a 2D Ising model, a square lattice Ising model. But in principle, we could have this on, and I think I showed this already when looking into numerical results for the critical exponents. In principle, you can put the Ising model in various dimensions and on various lattices. But independent of the choice of the lattice and the dimension, what's the same is that you describe the system with this Hamiltonian. This looks pretty simple. Luckily it is, specifically regarding explicit solutions and also in general, like when we go to the more powerful methods. This will typically be our toy model where we explore the results of it. And you may be wondering, is this a useful model at all? And it turns out, indeed, it is. It is really, despite its simplicity, it's a model that's very, very successful in describing a broad scope of materials and phase transitions. So let me just list a few applications. The very obvious is magnetism, right? Because that's what we're looking at. And here, the SIs really represent the spins, and H, the external field. And then the sum over all spins is the magnetization. And then what kind of magnet I'm describing now depends on the choice of my coupling constant here. So if my J is positive, that means that the Hamiltonian favors state where also SI, SJ give rise to a positive number, because then we have two positive terms and there's a minus sign here. So if you minimize your energy, that would be by spins being the product of two spins giving 1. So that could either be achieved by +1 times +1 is 1, or -1 times 1 is 1 is 1. So it's a parallel alignment of spin that is favored in this case. And so here we're talking about, this is then a description of a ferromagnet. We can also have the scope of J being negative. And that would then favor anti-parallel alignment, right? So that you have plus, the favored state would be one side being in the +1 state, and the other one, the neighboring ones, being in the -1 state. So that's the anti-parallel. Alignment. That's T small. And this would give rise to a checkerboard pattern, and represents anti-parallel magnets. And then obviously, just to be conclusive, we can also have J equals 0, right? So we have no interaction. And that's kind of boring, because if there's no interaction, then we also have no phase transition. So that's yeah, that's the boring case. And so when I explored like what are the states that this system would describe, I always mentioned that this would be favorable at small temperatures, because if we increase the temperature, obviously fluctuations will become more and more important. And so at a high temperature phase, I have a disordered paramagnetic phase. So there's a lot of fluctuations, so spins are not aligned anymore. I'm giving, by providing temperature, enough thermal energy into the systems that the spins will happily fluctuate around and have a paramagnetic phase. So for both, independent of the choice of J, as long as J is non-zero. Oh, that's actually for all T large. I have a disordered magnetic phase with no preferred magnetization. Okay, so that's kind of the obvious, right? So Ising model, magnets, but it's by no means the only one. Let me actually, so this was magnetism. Okay, let's keep going. I alluded to that already. So apparently you can also describe binary alloys. An example where you really have a fit of data to experimental data is beta brass, which is an alloy that is consisting of copper and zinc. And so to describe now having an alloy where I have atoms that are maybe either made of copper or zinc, and how they assemble in a structure together, I can think about them as in this picture where now the say the blue ones are copper and the white ones are zinc, right? And so the question is, how do, depending on the interaction that copper and zinc have to each other, how do they rearrange on, how do these atoms arrange on a lattice? And so then my SI is, say, either A for zinc, for copper, so that would be represented by, say, +1, or they are in a state B, which for beta brass is zinc, and that would be represented by the -1. And so copper and zinc form body-centered, so BBC lattice alloy. And as temperature increases, A and B can interchange their lattice spots, so they can really move around in the lattice. If I think about this application, I'm going to write down the Hamiltonian that would describe like this interchange that's possible between A and B, copper and zinc. And then we can see that we can map this actually back to the Ising model. And that's one example of many of like how you can start out writing down the interactions that you may have in a system, and then you can see that you can map it to an Ising model, or ones of the more complicated ones, which I'll introduce as we keep going along. So as the temperature increases, A and B interchange lattice sites. And so we can enumerate the exchange energies. If A and A change spots, B and B, and A and B. And so for that, let's box this. My Hamiltonian becomes, I have now an interaction for A and A, which again, I enumerate over nearest neighbors, and I write as 1 plus Si, 1 plus Sj, meaning that it's this term is non-zero only for Si equal +1, right? So if Si is equal +1, I have a 2 here. If Sj is equal +1, I have another 2 here. I have 2 plus 2, so I normalize by 1/4 to normalize for the factor of 4 that I get. And if just one of these spins is in the minus state for state B, I have 1 minus 1, which is equal to 0. So either term will be 0, and then the product obviously is also 0. And so in a similar fashion, I can, sorry, and there's a minus sign. In a similar fashion, I can write down the interaction between B and B, noticing now that B, I denoted with -1, so I write this as 1 minus SI minus SJ. Well, then this term is only non-zero, only for SI -1. And then we have an interaction term between A and B. Again, summing over nearest neighbors. And so to make sure that I have, again, either the A and the B state interacting, I construct that as S1 plus SI is representing the A state, and then 1 minus SJ is representing the B state, but that can also be the other way around, right? So I could also write 1 minus SI to represent the B state and 1 plus SJ to represent the A state, and accordingly, I normalize again. So this is just writing down the model for like these two states. And now we can readily reorganize these terms to see that they actually fall, we can map it to the Ising model. And so in the Ising model,
I don't understand how it can be only 0 for SI plus 1 when we have plus 1.
So my S can be plus 1 or -1. So we can just try out. If I have 1 plus -1, that's 0. If I have 1 plus 1, it's 2. So these are the two options I have for the spin. So this bracket is either 2 or 0. And the same is true for this one, right? Because if the SJ is 1, then it's a 0. And if the SJ is -1, I have 1 minus -1 is 2. So it's either 0 or 2. And so the largest I can have is 2 times 2, which is 4. So that's the normalization. Yeah. Okay. And if we go back to the Ising model, right? Remember that what we have here is a first term, which is the product of the SI and the SJ. So we can rearrange our terms here now to just accumulate here's an SI SJ term, here's an SI, and here SI SJ terms, right? And so we get, just lump out the quarter JAA plus a quarter JBB minus a half JAB. And then we have the second one was the sum over the linear terms, which we also get if we have 1 times SJ or 1 times SI. And so and I have a constant that's left over. That's proportionate to, it's a sum over 1. And so if we say we have n lattice sides, it's actually just 1. Oops, an n. Oops. That's n. So this is just a constant. And this prefactor we can now happily map on the Ising model if we just call it J, which we now learned from this bottom-up derivation, consists of the individual exchange energies. And then this is is arising from the exchange energies, but it sort of plays a role as an external field if we map it to the Ising model. And then as a note, here we have the sum of our spins in the system. Obviously, if I have the same amount of copper as I have zinc, then I have n over 2 plus 1s and I have n over 2 minus 1s. And then this is obviously 0 if I have an equal number of A and B. And so what we can see is now, okay, we've mapped the Hamiltonian, the constant we don't care about, because what's driving the interaction is now this interaction. So we mapped it to an Ising field without an external field, in the context of an equal number of A and B. And this is indeed an accurate description of a binary alloy, and you can really map experimental observations to predictions you get from the Ising model. As long as there are no impurities or empty lattice sites in the in your alloy. So it's accurate. And vacancies, yeah. Sorry.
Question.
Yeah.
But isn't like here the key difference that we only change arrangements, and in Ising model normally you can switch spins arbitrarily. Like it's possible in the partition sum to have an Ising model like in the for the magnetization that you have only spin ups. While here it's fixed how many spin ups you can have, and you can only change like the order because it's nearest neighbor, you can only change the ordering or
Yeah, sure.
so they still leave the same prediction because
in the case, so what happens is that this term here, sorry, this one is 0, right? If we have an equal number, which if you start from an ordered lattice, that would be the case, right? So it's in the absence of an external field. And so if you have the Ising model, in the absence of an external field, there is no, there's as much preferred alignment as you would, have through those thermal fluctuations. And it's the way of how you map it is that your exchange energy that you have here, if depends on obviously these choices, but you'd expect to arrive at a checkerboard pattern, right? So we'd be mapping this on the case of J being smaller than 0, where we expect an antiferromagnetic behavior. But it's incorporated in us looking at the Ising, like if you solve the Ising model, we actually, keeping in mind that we can choose J to be bigger or smaller than 1, we actually solve the binary alloy at the same time.
Okay. Yeah, I mean, at t equals 0, I agree, but if there are thermal fluctuations in the Ising model, I'm free to switch spins however I want. Like I can switch the amount of spins that is pointing upwards. Like here in, like as far as I understand.
No, but okay, so you have to, we did a mapping here, right? So we mapped the spin, if there is zinc at so you can have now at one lattice site zinc or copper.
Yeah, right.
If it's zinc, you say this is +1, and if it's copper, it's -1.
Yeah.
And so now the interaction is like, where are my zincs and my coppers? And if and you can't change how many you have +or -1.
Yeah.
But you won't have even if you turn on thermal fluctuations in the Ising model without an external field, you won't have a net magnetization.
Oh, okay.
Right. So you don't change the overall magnetic field. So the sum of having pluses and -1 will stay the same. The question is, how are they ordered?
Oh, okay. Okay.
But okay, so this is a good description, but what we're here considering is only the exchange energy from like switching locations in your lattice sites, and we throw out any vibrational modes that you can have on a lattice as well. There's that actually do have an impact. In atom positions, they bias So there's a bias that the configurations which will be such to have higher vibrational modes. So what we're neglecting in our Hamiltonian is the energy contribution of these vibrational modes. Which goes stronger with higher temperature. So in the end, it's only a good description at low temperature. The icing model is also a more valuable model for a lattice gas. And here, a gas, like we have individual atoms that are in space. So the two states that we have now is that either if we consider a space sort of aligned on a lattice, you either have an atom at a space at a site in your lattice or you don't, right? So you have occupied states and unoccupied states. And again, we have two states that we can map now the spins to. So we can either have a lattice site occupied, which there's going to be a mapping. That's why I start with a T. So if it's occupied, I say T is equal 1, or if it's not, then I say Ti is equal 0. And then my interaction energy favors that neighboring sites are occupied. So the interaction between the gas atom leads eventually can lead to a condensation. Neighboring sites occupied. And then I have chemical potential that's favoring occupancies if it's positive, or vacancies if it's negative. Or vacancy. Smaller one. And so taking these interactions into account, we can write down the Hamiltonian, where we have the interaction favoring sites to be occupied, which I only have if Ti and Tj are both non-zero, right? 0 was the state where it's not occupied, where's the vacancy. So only I get a contribution to this energy term if the both are 1. And then we take care of the chemical potential as well, which is only acting on the individual lattice site. And so now we can map it to the Ising model by making the following transformation of saying Ti is 1 minus Si over 2, such that now my SIs are again either +1 or -1. And then my Hamiltonian can be rewritten as now plugging this in, right? Writing Ti as 1 minus Si and Tj is 1 minus Sj. Again, I get a term Si, Sj. I get linear terms and I get a constant term. So Si, Sj. Then I get the linear terms from here, which I will lump together with the term from the chemical potential. And the constant term. And again, we can identify now here, this would be our typical exchange energy. This is the applied field, and this is a constant. So these are the ones that you find mostly discussed in books, but I could actually, there's a plethora of phenomena that you can, so a lot of like a lot of dynamics where you can describe the system as being in two different states is being mapped on the Ising model. And just to give a very prominent example, for example, also neurons, neural networks. So if you want to describe the activity of a neural network, you only classify neurons as firing, as being active, +1, or dormant, not firing, -1. And again, you have this two-state system, and all of a sudden you can look at the dynamics. You can look at the phases of such a very complex system again. And I could go on. There's a whole long list of why we care about the Ising model. It's in a sense similar to the harmonic oscillator, right? It's also like your pet that you've been dragging along in your physics study, because it's the simplest model that we know a lot about. And so if you know one limiting case, like for example here in the binary alloy, right? So we can solve it for low temperatures, and we can map it to the Ising model. It's a very good map. And then we can look, okay, so if we go up to higher temperatures, we're missing out on the vibrational mode. So I can then do, a perturbation and figure out what's the impact of this additional interaction. And I'm doing a good job at making a prediction and understanding what's going on, because I know what really has to happen in this limiting case. And that's why the Ising model is really useful, because it's one limiting case that we can sort of make it part of the system that we're studying for whatever reason. Then we have a benchmark of, like, if I solve the full model and I take, and I send temperature to 0, I should arrive at the Ising model. Is this correct? Are my analytical results correct? Or if I have a simulation and I run in the simulation, I run it at low temperatures, I also expect, to find the analytical results that I know from the Ising model. And therefore, it's very, very powerful to have a system that we really know a lot about. But obviously, only having two states is a little short-fetched, right? So there's a lot of systems which have more degrees of freedom. And so the story goes that we then expand. And so, for example, talk about the spin 1 Ising model. Spin 1 referring, and you will revisit more on the problem sets. So here we have more than two states. So we have, for example, SI being +1 or -1 or 0. And then, just this little change of having one more can make the Hamiltonian quickly a little more evolved. Again, we have this local interaction, but in this context, we also add SI squared as J squared, the linear term, SI squared, and also these interactions are possible. So these are all potential interactions that I can have now that my system has 3 states, 3 states, 3 degrees of freedom. So I'm basically going up to the second order in an individual spin, in enumerating all of them, because if I were to take the third power of any of the spins, that's exactly the same as having the linear spin, right? +1 to the power of 3 is +1, -1 to the power of 3 is -1, and 0 obviously 2. So there's no contribution that we would get from terms with the cubic exponent. So therefore there's no SI to the power of 3 terms. And so obviously here we already have a much larger parameter space, because we don't only have H and J, but J, K, D, and L. And so we also have much richer phase diagram that we can described. A model that I actually encounter a lot is the Q-state POTS model. Here, the idea is that we just in general say we have Q states that are placed again on each lattice side. And so like this classical POTS model would refer to a Hamiltonian where I then have just an interaction between, again, nearest neighbors. And I favor the SISJ a state where similar kind states, like so if Q enumerates from 1 to 5, then 5s are close to 5s and 4s are close to 4 states, you know, with the color 4 are next to 4. So it's a chronic delta here, where we have a contribution for neighbors of the same states. And so a standard application would be, for example, demixing of you know, of two solvents. Like if you have two solvents together, and how would they demix, right? So you have an interaction that drives them to favor being next to their kind, and so you can describe these phase transitions of a demixing. One really prominent and very powerful application in the past 10-15 years has been the application to as a cellular POTS model to describe the dynamics of tissues and cells. So describe the cells in tissue. So, for example, you want to describe how an insect eye develops. So remember, an insect eye, you have these, it's this very geometrical, very nice pattern of these individual kind of hexagonal shapes that form these this beautiful big faceted multi like I don't know how many, like hundreds, thousands maybe facets that form the eyes of insects. And so what's at the origin of this is that you have just cells that are growing, that are underdifferentiated, and they sort of have to decide to say, like, look, you know, the 8 of us, we're going to form like one facet here, and those other 8 next to us, they're going to form the other 8 there, right? So how do these cells actually communicate to make sure that they fall in this beautiful pattern? And so the way you can describe this now with a POTS model is that the Q states represent the Q-1 different cell types that you have in your tissue. And you keep the last one for empty space, just in case. So then you can sort of model the dynamics of a tissue, which is, you know, again, mapping it on a grid. And then you say, okay, so I have one cell here that is all, this is one, all blue is would be one cell. And then I take another color, and this is the neighboring cell here, cell 2. And they would sort of be enumerated within the model as saying this is the Q equal 1 state. Oh, sorry, that's confusing. Let me just make a Q2. And this is the Q equal 1 state. And so I could, in a sense, like, you know, define as many cells I want to study in my simulation. And I just give them the Qs, and then I follow their dynamics by looking at their interaction. And so the nice thing is that you can really nicely now capture the interaction that cells would have with each other, because what cells do is they cells within an epithelium, like, you know, our skin, for example, they adhere to each other. So you have a cell-cell adhesion, but also the cells, they typically are not floppy and elongated. So there's a mechanical web, like a purse string inside the cell that tends to make the cell round. So there's a surface tension effect. But then in the end, you also can't like push a cell to be like tiny. A cell has a certain elastic modulus, right? And so the cool thing is that you can all map this into a single Hamiltonian that, again, reminds you strongly of the kind of spin models that we have, where we now have here Si, Sj, -1, which here this term would then represent cell adhesion, because it measures for a single cell, it measures what's my circumference. So how many neighboring sides do I feel, right? Because I'm enumerating of how many, how big my surface is. This is cell surface tension. And then the elastic modulus I can take care by adding another term, where I'm looking at the area of a state Si versus a reference area, which is like the typical size of the cell. So this just analyzes in cell area respect to preferred And so I feel strongly about, you know, giving you this example just to elucidate that while we'll, for the most of this course, talking about Ising models, and, you know, there's a certain extent you can care about magnets, you're not, right? You're really looking at a very universal property of how physics can come together to generate phase transitions that is applicable to a very broad range of phenomena. By no means limited to magnets. Just to add one more model, the ON or Heisenberg model to your list. And model as a generalization, which is now to think of an n component unit vector at each lattice side. So that would say that the SI depends is a vector, so it is SI1, SI2, whatever the discretization is, with all of the vector being of unit lengths, so normalized lengths. So if I sum over all the individual components squared, get it at 1. And so then we go back to the standard Hamiltonian for a magnet, where we have the exchange SI, which are now vectors, SJ, and now the external field also comes in a vector form. And so what here we allow now, if we have this three-dimensional vector, or like whatever dimensional vector in space, that we have we add that the spin can have a rotational symmetry. So without an external field at zero temperature, the magnets could be aligned all in this direction or all in that direction. That's the same energy that it would have. But as soon as we apply an external field, a certain direction is favored, and so I break this rotational symmetry. And so that's a good model to study this, the breaking of the symmetry as well. So allows for rotational. It's a generalization of the Ising model. Spin, and so there's special cases. So for not 2 dimensions, I'm sorry, put n equal 2. We talk about the XY model. And for n equal 3, we talk about the Heisenberg model. So n referring to the degrees of freedom of your individual spin in space, like how many degrees of freedom it can have, but not saying anything yet about the lattice they're living on. So the lattice, so the Heisenberg model, the vectors can have, are representing multiple states, but they can live both on a 2-dimensional square lattice or in a 3-dimensional lattice. So these are 2 different parameters to look at. Okay, so this concludes my enumeration of, hey, these are models. As I said, you will see more on the problem sets, but it's more to sort of, again, teach you some vocabulary so that you know the names of certain models, but also just to show the breadth of like the phenomena that we can capture when now looking at the Ising model, which will, as I said, follow us for quite some time. So I now turn to the scope of exact solutions as a model. And so the simplest system that we can think of is to solve the Ising model in 1 dimension without an applied field. So go to the at 0.
Sorry, quick question.
Sure.
You said about the sum over the components of S, so SI to the alpha, would be 1. What is that?
It's your unit vector representing the space as a unit vector. So if I say it's 3 dimensions, I take the X component, the Y component, and Z component, and I square that and I calculate the length of my vector, and that vector is normalized to 1. So it's or like 2-dimension, a vector has an X and a Y component. I take this the length of the vector as X squared plus X X squared plus SY squared, and then you would take the square root, but since I'm normalizing it to 1, I skip the square root because the square root of 1 is 1. Yeah. Okay, so that's the simplest thing to start with. So our goal is to derive the partition function, because if we have the partition function, we know it all, right? can derive everything else. Everything else comes from there. Okay. In one dimension, like typical states, I can think about, it's like having, just spins lined up in whatever duration, and I can numerate the sides because they're linear ordered. Swap it here to n minus 1 and n, say I have n's. Have n spins. And so in one dimension, that means since my spins are ordered, the sum over nearest neighbors, Si, Sj, is then actually a sum over I, if I have Si, Si plus 1. And I go start with I equal 1, and I go up to n minus 1. And so then I can write down my partition function as the sum over all possible states. Each spin can take 2 states, +1, -1. So I should sum over all of them. So I have S1 equal +1, plus -1. I have S2 +1, -1, and so on until Sn equal +1, -1. This is enumerating all states that we have in the system. And then we take the Boltzmann factor of minus beta h. The interaction is minus j, so the minus cancels, and I have minus j. Now here, summing from I to 1 to n minus 1, Si plus 1. And so the trick why we can solve this readily is to realize if I have an exponent of a sum, I can write this as a product of exponentials, right? So this actually is nothing else, this term here, as e to the beta j as 1 as 2, e to the beta j as 2 as 3, and so on, going unto e to the beta j as n minus 1 as n. And so what then I have to do if I want to sum over the states of these, so then we notice that so as like any spin inside, like S2, like if I sum over S2, it sort of really pops up. It pops up only in these exponents. So if we sum now over Sn equal +1 or -1 over beta j as n minus 1 as n, then this is e to the beta j as n minus 1 times 1 plus e to the minus for the opposite spin for Sn. And so that's nothing else as 2 times the parabolic cosine of beta j as n minus 1. But then I recognize that, so now I would need to look at what happens to the summing over the states of Sn minus 1, so which again can be plus or minus 1, right? But then we remember that the cosine hyperbolic cosine is symmetric about the origin. So it's the same if I have x or minus x, which means that Sn minus 1 being +1 or -1 is exactly the same energetic contribution. I just have to keep in mind that for every, I get a factor of 2 if I now sum over them. And so then I can readily write down what I have here is for the first summation over Sn, I get 2 for Sn minus 1 plus 1 and minus 1 plus h beta j. And then in principle, I'm still left with all the other sums, S1 equal plus 1 minus 1, S2 equal plus 1 minus 1, blah, 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 until now Sn minus 1 plus 1 minus 1. And so obviously now if I do the same summation for Sn minus 1, I get the same contribution, namely twice cos h beta j. And so in the end, we readily see that what we then have here is 2n minus 1 terms of exactly that contribution. And minus 1 up to summing over S1 equal plus 1 minus 1, because the last term, this one, is already taken care of by summing over S2, right? So this is still left over. And so the sum over S1, this one, the sum is still left over, but the number of states that we arrive here, so this is just equal to, so we have, this is 2 to the power of n plus h beta j n minus
1. Excuse me.
Yeah.
Shouldn't it be a 4, or am I missing something? Because you have a 2 of.
You have 2 states. I have a
Yeah,
plus 1 and a minus 1.
Yeah, no, but I mean, you have a 2 cosine h and then beta something in the upper side. So you already have a 2, and then you get the 2 from plus and minus 1. So shouldn't it?
Yeah, I have 2 to the power of n minus 1, and I make it a 2 to the power of n.
No, I mean, like before the.
This?
Yeah, up and then up again, like a bit. Yeah, right. This one, yeah. Here's a 2, right? Here's already a 2.
Yeah.
And then you get a second 2 from the summation. So shouldn't it be a 4 in total?
Ah.
This is what I'm asking.
It's 2. Maybe the argument I gave was wrong. So
no, this I think
oh, I didn't sum yet over the states. Sorry. So the argument I gave was wrong. So so what I'm doing here is I'm summing over these states. I don't sum over Sn minus 1.
Yeah, yeah.
But I recognize that this contribution that I get from this sum is actually the same for both configurations.
Yeah.
If I were to sum over Sn minus 1, which I haven't done yet. And now so I write down, like I can factor this out, the result of the sum over the states of Sn minus 1, states of Sn, factor out, become this, because it's independent of any choice of Sn minus 1. And then I sum over Sn minus 1. And then for the sum over Sn minus 1, I get exactly the same contribution. Yeah, and then it's all truth. Yeah. And I mean, you don't have to memorize, but we'll take this, you will revisit this exact result a lot of time as a limiting case that we can solve in, I don't know, 4 lines, to make sure that whatever else more complicated we derive, we end up here. Because that's the simplest whatever we can do. And now we become more adventurous, and we go to the one-dimensional Ising model with an applied field. Sure.
I didn't understand why in the second to third line, why the cos of x equal cos of minus x implies that.
Why this is true?
The Sn minus 1. No.
This one?
Why that means that we can take the S minus 1 out of the parentheses inside the cos.
So this is true because the hyperbolic cosine is a symmetric function over the origin. And so it means now if we look at this term, and what we, so if you want to say like a line that's missing would be writing down, how do I do this? I would now have, I'm considering now Sn minus 1 equal plus minus 1 e to the beta j Sn minus 2 Sn minus 1, and in principle I still have this term here too. right?
Mhm.
So now what I do is I say the values that Sn minus 1 can have is +1 or -1. So if I just plug this in, then these two terms are actually identical.
Yeah.
So I can just pull it out. Doesn't matter. I can move it here as this prefactor.
Oh, okay.
That's what's happening. Yeah. Okay. More questions? Perfect. So now we turn to the one-dimensional. With and so here the first powerful tool comes into play, namely the transfer matrix approach. Okay. So the problem that we want to solve is now we consider a Hamiltonian where we have what we already dealt with, I minus 1 to n minus 1, si plus 1. But now we add this external field and have another contribution. And since now we have a sum in the exponent, we can't necessarily go ahead and do this nice factorization that we did before. And so, but we can still solve it with just what's called transfer matrix approach. Let me first specify the boundary conditions. So as it's the simplest case, we start with the periodic boundary conditions. So, which means that Sn plus 1 is again S1. So you kind of think of, basically we have a circle. Oh God, a circle. Yeah, kind of. And now if I go in and I look at the spins, then that are aligned, that are sort of on this lattice that forms the circle, then I would go from S1 minus 1, Sn, and then here I'll be back at S1, S2, and so on. Again, the goal is to have the partition function. Oops. Which is summing over all states. And now we have here beta J. And what I do is the trick that I want to do is I want to write this now as a sum of, as a single sum. And what I as a single sum, where I only have Si and Si plus 1 popping up. So I kind of want to symmetrize this exponent. And the way I can do this is to write this as minus 1. Minus 1. And then I'll write this as actually, I to the power n minus 1. And now I have this beta J as I plus 1 previously. And now I have another contribution here from beta H over 2, where I now symmetrize to have Si plus Si plus 1. So what I do is so I'm summing over S1, Si1 here, and I can here I sort of sum over Si, say S5, I sum twice, right? once as when I sum over I equal 5, but also when I sum over I equal 4, right? Because then this term is as 5. And so I compensate for that by having this 2 here. So I didn't change anything, but I symmetrized the Hamiltonian such that I'm back to a description where I have a sum in the exponent, which I can factorize. But now I have to pay attention that this factor that I have here is actually summing over 4 different potential realization, right? So I only have here Si and Si plus 1, but Si can be +1 and -1, and Si plus 1 can be +1 and -1. So I have 2 combinations for each of these 2 spins. So 2 times 2, I have 4 different combinations that I should consider here. And an efficient visualization of this is to write this as a matrix product of, in this case, a 2 by 2 matrix. I'm going to define it in a bit. And in the end, I'm going to have here a product of individual transfer matrices that are representing this exponent for looking at SI 1 to 2, 2 to 3, 3 to 4, 1, 2, 2, 2, 3, and so on. S and -1 and T, and then just to have the symmetric boundary condition, I go from N again to 1. And so where here I define the transfer matrix T I plus 1 as e to the power of beta J Si plus 1. Sorry, has to be an exponent. And so just to visualize, this actually means that for T I plus 1, I have to consider Si being 1 and Si being -1, and I have to consider Si plus 1 being 1 and Si plus 1 being -1. And so the entries that I can have in this matrix are now, for both of them being 1, I get e to the beta J plus 1 plus 1 is 2 beta H, so J plus H. And the same is true if they are both, no, it's not true. And for both being -1, I have beta J, but a minus H contribution here. And if one of them is +1 and one of them is -1, then this term cancels out. And so here I only have the contribution minus beta J. And so this is an efficient enumeration of all potential states, right? And so now here I'm really looking at the product of all these different states. And so just a few comments on the transfer matrix approach in this case now is that if we look at this, and that's why it's really powerful here, we see that once we enumerated these different states, that this matrix is actually independent of the choice of I. So it's the same for 1, 2, and this as for 3, 4. So we can actually call this T without dropping the indices, because note entries are independent of I. And also note the size of the transfer matrix is the number of spin configurations. So if we, for example, think about the would be Q times Q for the Potts model. But you could use this to enumerate all of them. So now we are just change the representation of these exponents into which used to be, you know, products over e to the powers into these transfer matrix. And it allows us to now efficiently sum over states. So for example, if I now have S2 equal plus minus 1, I have to consider T12 times T3, 2, 3, which we know is actually the same as 2, sorry. Since we're taking we're multiplying them both, what we arrive at is that this summation is actually the way of writing down our matrix multiplication. So this is just T1, 3, the transfer from 1 to go to 3 squared. And since this is actually independent of the choice of the indices, this is T squared. There's a type of my notes. And so obviously now if I sum over all these different realizations, I can write the partition function as going from 1 to 3, going from 1 to n. So let me just leave out the S1 multiplication going from 1 to n plus 1, which would be n steps in between on our circle periodic boundary conditions. And then in the end, taking the sum over all these taking the matrix products, evaluating S1 plus 1 and S1 minus 1 will be actually given that this here the state n plus 1 is actually, we're looking back, right? We're looking back to as n plus 1 is just S1. So what we're doing here when we perform the last summation of states is that we're looking at the entry of this matrix, which is the matrix product, as of the diagonal entries, right? S1 being 1 or S1 being minus 1. But looking at the two contribution of the diagonal matrices, it's just taking the trace of our matrix. So this is then taking the trace of T to the power of n, which, yeah, let me add. So this is the, this was the sum over diagonal entries only. That's a trace. And so this is very cool because now what we need to do, and really we can actually say a lot about also very different system. So if we're able to find this transfer matrix, then the partition function for periodic boundary conditions is just given by the trace of the transfer matrix to the amount of lattice sites in 1D. And so now to take the trace, what the trace actually is, it's just the sum over the eigenvalues, right? So say I define lambda plus and lambda minus as the eigenvalues of the transfer matrix T. Then I know that the trace of T is just lambda plus lambda minus. And obviously, then it's also easy to say what's the trace of T to the power of n, because that's then lambda plus to the power of n plus lambda minus to the power of n. And so we can do this, right? We can determine now the eigenvalues of our transfer matrix by looking at e to the beta j plus h e minus, oops, sorry, there's the minus lambda. Listen. Minus lambda e to the minus beta j e to the minus beta j, and then here beta j minus h minus lambda, taking the determinant, we arrive at lambda square minus lambda e to the beta j plus h plus e to the beta j minus h, and the linear terms are then plus e to the 2 beta j minus e to the minus 2 beta j. And so this needs to be 0. That defines our eigenvalues. And so we can read this off because we know that this needs to factorize in lambda plus 1 minus 1. So, which is equivalent to lambda squared minus lambda. We can see that lambda plus lambda minus, this is equivalent to 2 beta j minus e to the minus 2 beta j, which is a positive number. And then lambda plus minus lambda minus, sign error, quickly check. Minus, there's a minus here, that should be a plus. It's a plus. This I can now read off, that needs to be this term. Yep. And so that we can actually factorize, we can pull out the beta j e to the beta h plus e to the minus beta h, so that we can see that this function, also without having specified anything, is bigger than 0. And so why are we doing this instead of just, you know, writing down the solution? Because there's one important insight that we can gain on it already, because we defined our partition function to be the sum of lambda of the 2 eigenvalues to the power of n, right? So I can write down my partition function factoring out the lambda plus eigenvalue as 1 plus lambda minus divided by lambda plus to the power of n. And now, since we see that these 2 contributions we can readily read off are both positive all the time, we see that lambda plus has to be bigger than lambda minus. We can make this deduction. And so we know that if we send n to infinity, that this contribution should become negligible because this is smaller than 1. We know that the partition function is governed by the largest eigenvalue. I know it sounds silly, why are we doing this in this case? Because obviously we can just actually solve this quadratic equation here. The reason why I want you to see this is that we can also write down a partition function for a Q state Potts model, where all of a sudden you have a Q times Q value. So we're not looking at evaluating 2 eigenvalues, but Q plus 1. Q eigenvalues, sorry. We're looking at Q eigenvalues. And this might be much more clumsy task to then solve this Q's order equation to find all the eigenvalues. But what we see here now already is that there's no need to do so, because the partition function, at least for an infinitely large lattice, is actually governed by the largest eigenvalue anyway. So if I have a means to determine the largest eigenvalue, I'm actually golden already, right? So I can know a lot about the system. And so that's the insight that we can gain here already. This goes to 0 for n to infinity, and so ln z for n to infinity is then actually just n ln lambda plus. Okay, but in this case, I agree. We can just write down the two eigenvalues if we were to care, which I do over 2 plus 1. And so here now the square root, if you look at this one, so the square root contains effective have a 2 beta j if I factor out the at here times e to the 2 beta h plus e to the minus 2 beta h plus 2 if I evaluate the square. Sorry. And then here I can 4 e to the 2 beta j plus 4 e to the minus 2 beta j. And so we can lump this together by noticing that which 2 times these 2. We can lump together these terms to have e to the 2 beta j minus 2 then, and I'm copying down the remaining term. And so then I can simplify this bracket again to become e to the beta h minus e to the beta h minus beta h plus sorry, square missing. And so why am I doing this? Because now what we have written down here is just the hyperbolic sine. So this is nothing else than a correct normalization for 2 beta j sine h beta h squared plus 4 e to the 2 beta j. And so with that, I can simplify our eigenvalues up there. That was a long, clumsy expression into also recognizing what we have here. If I factor out the e to the power of beta j, I have a hyperbolic cosine left, right? So I get e to the beta j cos h beta h plus minus e to beta j and the 4 cancel with a half. And sorry, one more step. Plus. That's the most compact way. And so since we have them now, we can actually determine the free energy per spin for n to infinity as Okay, let me introduce this notation, small f as big F, oops, over n as is then minus kbt limit n to infinity of 1 over n ln z, and that's then minus j minus kbt ln and the bracket's closing. Yep. And so we're already very happy about this result. It already looks clumsy, I agree, but hey, it's an analytic solution in the limit of large n. And obviously you could write down also the less contributing negative and not negative smaller eigenvalue to have a really exact result. But this is what we're gonna actually work with to then use this to study the phases of the system. But now we first unfold the power that we used now a new method to solve the Ising model with an external field. While we were very happy about our solution that we could do just by simple enumeration of the Ising model without an external field, we can now check that our result makes sense. So we check what happens now in the result for sending the external field to 0. So we look at f at h equals 0. We do this, we have still minus j minus kbt ln of cos of 0 is 1 plus the sine of 0 is 0, and this sine h, I'm sorry, sign. So we're just taking the square root of the exponential, so that's minus 2 beta j. And now so since j can rewrite as kbt ln of e to the power beta j, this becomes minus kbt ln e to the beta j for the first term, plus ln copying down the second term, and now lumping them both together. We see that we have here now beta j plus e to the minus beta j, which we can identify as a hyperbolic cosine again to arrive at minus kbt ln of 2 cos h beta j, knowing that this is, we would identify as the z of h equals 0, right? Okay, so then we scroll back. To see that, sorry, that's z. So I normalize by n, right? Remember, it's z over. So here we have the full z, and if I take the ln, the n becomes in front, and if I take the free energy per spin, I divide by n, so the n drops out. So what is important to find the functional dependence that I have 2 cos h beta j. Back, there we go. So we assured that our transfer matrix approach got us to a result that we can match in the limiting case, and we found the first powerful method to have exact solution, albeit as you can see, only applicable to very specific systems. But in principle, we will see how you can generalize this transfer matrix approach for more complicated systems, because and that's the most important thing, you only have to look at the largest eigenvalue, and that makes it a powerful approach that we can learn just looking at the Ising model. So with that, that would conclude the material for today. I will stop the recording and be happy to take more